Okay, so hi everybody. Can everybody hear me? Let me see if I can. Okay, great. So okay, so this is lecture 18. Okay. So and in this lecture, we're actually gonna. Okay, so somebody has a question. Yeah, hi. Do you have a question? Hello. Do you have a question? I can't hear you. Okay. So what we're going to do in this lecture is we're going to shift to a different aspect of linear algebra, which is different from what we've been doing so far. So far, all of our discussion of linear algebra, certainly all our discussion of vectors, is concerned with when some vector is a linear combination of some other vector. Right? So far we've basically been studying linear combinations. And we've asked questions like, well, when is a given vector a linear combination of these other vectors, right? But we've only really asked, we've only really asked questions which can be phrased in terms of equality of linear combinations. And what we're going to do now, which is the topic of chapter 6, is add a couple of new concepts to linear algebra, which are going to be related to geometry. Specifically geometry of Rn for now, okay? So we're going to go back to our good old favorite vector space Rn. And what do I mean by geometry? Well, I mean concepts like length, angle, and distance. So concepts that you've maybe studied in Euclidean geometry in high school. And so far we don't have a way of saying what is the distance between two vectors, right? Or what is the angle between two vectors. We only have a way of talking about linear combinations. So what we're going to do now is develop these geometric concepts. And so there are two key new operations on vectors that allow us to define geometry. So the first is the norm. So given vector, call it U, the norm of the vector is defined to be the generalization of how we measure norms in R2 and R3, namely the square root of the sum of squares of the entries of the vector. So in particular, I'm imagining the vector has 4 U. And this is clearly a non-negative number, and this is going to be my notion of length. So this corresponds to length of a vector. And there's only one vector that has length 0, that's the 0 vector. And this gives me a notion of distance. As soon as I can measure distance, I immediately get a notion of, as soon as I can measure length, I can measure distance just by taking the length of the difference. So norm of U minus V, this is going to be the distance between two vectors, U and V. And it's easy to see that the distance is 0 only if the vectors are the same. So this is a generalization of some familiar concept from R2 or R3 that you're used to. But really, the more fundamental concept than length is actually another new operation you certainly studied if you took Math 53. And that new operation is the dot product. So given a pair of vectors, so let's say U has entries U1 up to UN, and V has entries V1 up to Vn and Rn. The dot product for their dot product is defined to be U dot V, which is just U1 V1. Sorry, this is not a vector anymore. This is just a number. Plus U2 V2 all the way up to UN Vn. So the sum of products of corresponding entries. And another way to write this in maybe in more matrix type notation is this is equal to the product of U transpose and V, right? So remember, vectors in Rn are defined as column vectors. U transpose is actually something we haven't really seen much of before. It's a row vector, right? If you view this as a matrix, U transpose is the n by 1 matrix, entries U1 through UN. And then if you literally look at U transpose times V, that's an n by 1 matrix, I'm sorry, a 1 by n matrix, it's a 1 by n matrix. That's a 1 by n matrix times an n by 1 matrix, which gives me a 1 by 1 matrix, otherwise known as a number. Okay? So this is the key new operation, the dot product. And it says product, so it's tempting to think of it as a way to multiply vectors. But really, it's not multiplication in the same sense of multiplying numbers, right? So if you multiply two numbers, then you get another number, and then you can multiply that by another number. Here, if you multiply two vectors, you don't get a vector, you get a number, right? So you shouldn't really think of it as multiplication, as an analog of multiplication. It's just another operation that that gives you a number given two vectors. And there's a nice relation between the dot product and the norm, which is that, well, if you take the norm of a vector squared, that's just the sum of squares of its entries, right? And that's just the dot product of the vector with itself. So actually, the really fundamental quantity here is the dot product. Once you have the dot product, the norm is just the dot product of a vector with itself. So okay, this just looks like some algebraic operation. What nice properties does it have? So let's look at the properties. We can easily check from the definition. So one is, well, it has this distributive property. So U dot E plus W is U dot B plus U dot W. These are really easy to check, so I won't do proofs. The second is U dot a scalar multiple of a vector is just that scalar multiple times the dot product. And then the third property, which is also obvious, is that U dot V is the same as V dot U. Okay, so these are some fairly trivial algebraic properties. But I mean, the reason the dot product is so important is that it actually encodes, we saw earlier that it encodes length, right? Because the norm is just the dot product of a vector with itself. But the somewhat surprising thing is that it actually also encodes the notion of an angle. Well, so suppose you have two vectors U and V in some Rn. So I know how to talk about the lengths of these vectors, right? The lengths are just these norms, which we saw are given by the dot product. But now we can ask, what's this angle theta, right? So two vectors in Rn, they span a two-dimensional subspace. So that's a two-dimensional plane. Yes, do you have a question?
Yeah, just really quickly. When you say that the dot product encodes the length, isn't it the length squared?
Yeah. The length squared for sure.
Okay,
So
okay.
all I mean is, you given the dot product, you can derive the length.
Okay, got it.
Yeah.
Cool, thank you.
Yep. Okay. So now the neat thing is that actually the dot product also encodes the angle between the vectors. Here's an important geometric fact. The fact is that the dot product u dot v is equal to the product of the norms times the cosine of this angle. Okay. The proof of this is in the book. We won't prove this. But okay, I mean, maybe I'll just show you an example just to make sure we're all on the same page. So let's say I have two vectors, 1, 0 and 1, 1 in R2. Well, I can draw these vectors. I'm used to drawing them. So U looks like this, and maybe V looks like this. And well, I'm interested in the angle between them. So I know from prior experience that this angle is pi over 4. But let's just check that the dot product gives that to you. Well, the dot product of u and v is 1 times 1 plus 0 times 1, which is 1. The norm of u is square root of 1 squared plus 0 squared, which is 1. The norm of v is square root of 1 squared plus 1 squared, which is root 2. And so according to this fact, which according to this fact, I should have that the, sorry, it shouldn't be red. I should have that the cosine of the angle between them should be the ratio of these numbers. So 1 over root 2, which is actually cosine pi over 4. Okay, so this checks out. So not only does the dot product encode lengths, it also tells you what the angles are. Okay. And so this is the sense in which you can use the dot product to do geometry. Now we can, given two vectors, we can figure out their angle and length by computing dot product. Any questions? Okay, so we're not really going to be interested in general angles that much in this course. There's one particular situation that's extremely important, which is when the angle is 90 degrees. This has a special name. U and V are orthogonal. So that's just a fancy word for perpendicular in this context, if the dot product is 0. Okay, this is the definition of perpendicular in high dimensions, right? So perpendicular, we know how to visualize it in 2 and 3 dimensions, right? We learned that in high school. But how do you visualize it in 1,000 dimensions, right? Or how do you even define it? This is the definition. And why is this a reasonable definition, right? It's just some funny formula with these two vectors. Well, if you believe the cosine interpretation, 0 is indeed cosine pi over 2, right? But since I didn't give you the proof, let me just show you that this definition of orthogonality satisfies the most important theorem about orthogonal vectors, about perpendicular vectors, which is Pythagoras theorem. So what does Pythagoras theorem say? Well, it says that in a right triangle, the square of the length of the hypotenuse is the sum of squares of lengths of the side. So in terms of vectors, what does this look like? Well, let's suppose one of the vectors is u, and let's suppose you have some vector v that's orthogonal to this vector, so 90 degrees. And now this is going to be the hypotenuse, right? So if I write this as a vector, this is the vector v minus u, right? That's the picture associated with this. And what the theorem says is if u dot v equals 0, then the norm of u squared plus the norm of v squared is equal to the norm of u minus v squared. Or okay, let me norm of u minus v is same as norm of v minus u, but let me just write it as v minus u since that's okay. This is our familiar Pythagoras theorem. And what I'm going to do now is I'm going to prove it purely using the algebraic properties of the dot product. And that's evidence that the dot product is the right geometric notion. Well, what's the proof? Well, okay. Norm of v minus u squared. So what's the norm squared? It's just a dot product of a vector with itself, right? So that's v minus u dot v minus u. That's what we observed on the previous slide. And now by the distributive property, you can just FOIL this. And you get that this is v dot v minus v dot u minus u dot v plus u dot u. But now, what was our assumption? Our assumption was that the vectors are orthogonal. So if this is true, these terms just go away. And what's left is indeed the norm of v squared plus the norm, which completes the proof. One-line proof, the one-line calculation. And the point of this proof is that this means that this notion of orthogonality satisfies Pythagoras theorem, which, I mean, if you take higher math, Pythagoras theorem really is the definition of Euclidean geometry. I mean, maybe that doesn't make sense because you haven't thought about other kinds of geometry yet, but really, if you have a system of lengths and angles that satisfies Pythagoras theorem, that is Euclidean geometry. Okay, so this shows that this is consistent with our geometric intuition, in particular Pythagoras theorem. Yes.
Quick question. It works in like any dimension, right?
Yeah, this is in any dimension. See, in the proof, I never used what n is, right?
Yeah.
I only use the properties of dot product. That's the beauty. It works in any dimension. Yep. Okay. So that's the dot product and orthogonality. Now I'm going to talk about, so I told you what it means for two vectors to be orthogonal. Now I'm going to talk about a whole set of orthogonal vectors. Okay, so what's the definition? Well, it's what you think of it. It's what you think it is. It's a set of vectors so that all pairs are orthogonal. A set of vectors that's the u through u sub p in Rn is an orthogonal set if all pairs of distinct vectors are orthogonal. Ui dot uj equals 0 whenever I is not equal to j. Okay, so all it means is all pairs are orthogonal. Okay, so what are some examples of this? Well, let's just take the standard basis vectors in R3. Okay, it's an orthogonal set. If you take any two of these and compute the dot product, it's 0. Also geometrically, we know this, but remember, orthogonal just means the dot product is 0. Here's a maybe more interesting example. Let's take these other three vectors. So 2, -1, 0. 1, 2, 1, and third vector is let me just check. Okay. -1, -2, 5. So these are vectors in R3. And now if I compute the pairwise dot product, so u1 dot u2, well, that's 2 minus 2, which is 0. What's u1 dot u3? That's -2 plus 2, which is 0. And what's u2 dot u3? That's -1 minus 4 plus 5, which is also 0. So indeed, this is an orthogonal set. And if you were to draw these vectors in R3, you would indeed see that they are perpendicular. So there's one more piece of terminology here which comes up. Orthogonal set means the dot products are 0. It's an orthonormal set if additionally, so if it's orthogonal, but all the norms are 1. Okay. So, for example, the first example here, I have that the norm of E1, I can compute it, is 1, which is also the norm of E2 and also the norm of E3. This first example is, I mean, they're both orthogonal, but the first example is which is a special type of orthogonal set. The second example, okay, I'm sorry, I don't know why this, okay, the colors are, the second example, well, I can compute the norms, right? Let's just compute the norm of the first one. That's square root 4 plus 1, which is square root 5, which is not 1. So that's an example of something that's orthogonal, but not orthonormal. Because the norms are not 1. So I could easily make it orthonormal by dividing every vector by its norm, right? So can make orthonormal just by considering u1 divided by its norm, u2 divided by its norm, and u3 divided by its norm. You can always do that if the vectors are not 0, right? So by the way, the definition of orthogonal set, it could include a 0 vector, right? 0 vector is actually orthogonal to everything. So this dot product with everything is 0. But you can always make orthogonal set of non-zero vectors orthonormal just by scaling. So by that's an orthogonal set. So now I want to connect this to one of the key concepts we learned about in the course so far, which is linear independence. So let's prove an important theorem. The theorem says if U1 through UP is an orthogonal set of non-zero vectors, okay, so orthogonal but can't include 0, then it's a linearly independent set. Let's say this is an Rn. Okay, so this connects orthogonality, which is this geometric notion that pairs of vectors are perpendicular, to a linear algebraic notion, which is linear independence. So it's an important theorem. And let's see the proof. Well, so suppose I have an orthogonal set. So suppose the vectors are orthogonal, and suppose some linear combination is 0. So suppose C1 U1 plus C2 U2 all the way up to CP QP is 0. Well, my goal is going to be to show that the coefficients are 0. So we'll show that all of these scalars, C1 equals C2 equals CP are 0. Yes, so there's a question. Yes, do you have a question?
Yeah, is this an if and only if condition?
Nope. So the question is this if and only if? So this is saying orthogonal implies linearly independent. You're asking, does linearly independent imply orthogonal, right?
Yeah.
Well, let's just write it on the next slide for now. The answer we've kind of already seen is no. Because consider these vectors. Consider these two vectors. These are linearly independent, right?
Right.
But they're not orthogonal. Because, I mean, even geometrically, they look like this. So orthogonality is a stronger condition than linear independence. That's what the theorem is saying.
Thank you.
Yep. Okay, so now let's go back to the proof of the theorem. So again, you have this linear combination that's 0, and you have to show all the coefficients are 0. Well, how would I do this? So the trick is I'm going to take a dot product of, this is what I know, right? I'm assuming this, and I need to show the coefficients are 0. Well, what happens if I take a dot product of the whole thing with 0? Consider U1 dot this whole thing. Well, that better also be 0, right? Because any vector dot to 0 vector is 0. But now, by the properties of the dot product, I can, distribute the dot product over the individual terms. And I get that this means that C1 times U1 dot U1 plus C2 times U1 dot U2 all the way up to CP times U1 dot UP is 0, right? Just by taking the dot product. But now, watch this. My main assumption was that the vectors are orthogonal. That means if you have two distinct vectors, the dot product is 0. So all these other terms go away. And I just get that C1 times norm of U1 squared equals 0, because everything else disappeared. That's the beauty of orthogonality, that if you have a bunch of orthogonal if you have an orthogonal set and you have a linear combination of them, if you take the dot product with one of the vectors, all the other vectors vanish by orthogonality. But then, well, I assume that the vectors are not 0, so that means this norm squared is not 0. So that means C1. So I just proved C1 is 0. So any thoughts about how to prove C2 is 0? Yep.
Just take the dot product with B2.
Yeah, just do the same thing with U2. So similarly, if you take U2 with the dot product, if you take a dot product with U2, sorry, CP, this will imply C2 is 0. And finally, you'll just do this P times and get that CP is 0, and that's it, you're done. That means they're linearly independent, right? The only non-trivial linear combination, there is no non-trivial linear combination that gives 0. So the summary of this proof, I mean, the meaning of this proof goes back to this question. And really what it's saying is that orthogonality is stronger than linear independence. And another way to think about it is, well, linear independence, what did it say? It said no vector is inside the span of the other vectors, right? Well, orthogonality says that every vector is actually perpendicular to the span of the rest. Is perpendicular to the span of the rest. Okay, so this is a stronger property than linear independence. Okay, so we defined linear independence, and okay, naturally, once we have a stronger notion of linear independence, we can have a stronger notion of a basis. This brings me to the next definition, and the definition is that wait a second. Just a sec. Yeah, okay. So I want to make sure I was recording. Okay. The definition is that a subset of Rn, subset of vectors in Rn, is an orthogonal basis of a subspace if the following two things hold. One, same as before, the span of the vectors is equal to the subspace. That's the same as before. But the new thing is we strengthen linear independence to now be orthogonality. Of non-zero vectors. You have to exclude 0, right? So that's an orthogonal basis. And similarly, as before, I mean, this is just a normalization thing. If the vectors are additionally orthonormal, which just means the norms are all 1, then it's called an orthonormal basis. Okay. So that's a new, well, better kind of basis. And let's see why it's in some ways better than just a plain old, just linearly independent basis. So let's look back at our example. Or let me actually do it on a new slide. Let's look at the same example again. We have the same three vectors, u1, which is 2, -1, 0, which is 1, 2, 1, and u3, which is -1, -2, 5. Now these are non-zero orthogonal vectors, so they're linearly independent. There are 3 linearly independent R3 vectors in R3, so this is an orthogonal basis of R3. Okay. And okay, what do we do when we have a basis? Well, we can express every vector in R3 uniquely as a linear combination, right? So that means I can express uniquely some given vector, let's say the vector 1, 0, 1, as some linear combination of these vectors. Okay, we've done this for a while now. But now you can ask the question, well, how do you find the coefficients, right? So to find these coefficients, well, traditionally you just do row reduction, right? I mean, given linearly independent vectors, we know how to express a vector and their span as a linear combination of them with row reduction. But the nice thing is now with orthogonality, you can do something that's much easier. So this is one of the benefits of orthogonality. It actually lets you avoid row reduction. So what's the idea? Well, it's very similar to what we did in the proof, right? So let's say I want to find C1. Well, what's the idea? I somehow would like to isolate that coefficient C1, right? Well, what happens if I just take a dot product of both sides of the equation with U1? I have U1 dot X. So on one hand, so maybe I'll write it over here. That's just a dot product of these two vectors, right? 1, 0, 1, and 2, minus 1, 0, which is just 2, right? So U1 dot X is 2. On the other hand, I also know that it's equal to U1 dot this linear combination that I don't yet know. But again, by the same trick, by orthogonality, these go away. And so I get that this is literally just C1 times norm of U1 squared, which is C1 times 5. But now I can just solve for this, right? That means C1 is equal to 2 over 5. Yes, do you have a question?
Yeah, sorry. Just as a follow-up to that, could we also view it as sort of a projection onto like V1?
Yes, so your question is, can you view it as a projection? You can. That's what we're going to do later in the lecture. That's a more sophisticated way of thinking about it, but yes.
Thank you.
Yep. Any other? Okay, so we solve for C1. Similarly, we can solve for C2, right? Similarly, C2 is again going to be a certain ratio, right? It's going to be U2 dot X divided by norm of U2 squared, which is in this case what? So U2 is 1, 2, 1 dot the vector 1, 0, 1. Norm of U2 squared is going to be is just going to be 1 plus 4 plus 1, which is 6. So this is a third. And then C3 is going to be norm of inner product of U3 and dot product of U3 and X divided by norm of U3 squared, which is okay, so U3 dot X is minus 1 plus 5. And norm of U3 squared is a little more complicated. So it's 25 plus 4 plus 1, so that's 30. That's 4 over 30, which is 2 over 15. Okay, so the bottom line is, the bottom line is we managed to solve this problem without row reduction, right? We managed to express this x as a linear combination of these vectors. So you get 2/5 times the first vector plus a third times the second vector plus 2/15 times the third vector without row reduction. And actually something much easier, right? Just some basic arithmetic. So this is what you get out of having orthogonality. One of the things, you get many things, but this is the first one, that you can easily express things as linear combinations. And I should say it becomes even easier if it's orthonormal, right? Because it's even easier if all the norm squareds are equal to 1, right? Because all the denominators just become 1. So that's a further benefit of orthonormal, that the calculations become even easier. Okay. So what's the general theorem here? There's a general theorem. You can always do this. It's not an accident. So let's write the general theorem. And what it says is if U1 through UP is an orthogonal basis of some subspace W, and you have some vector in that subspace, then the linear combination always looks like that. So y is equal to U1 dot y over U1 squared times U1. Sorry, this looks like a V plus U2 dot y over U2 squared, U2, all the way up to norm of UP dot y, sorry, dot product of UP and y over norm of UP squared times UP. Okay. And maybe speaking to Castro's question, so what is the meaning of this? So, well, so what's the geometric meaning? So I'll just draw the picture in R3, partly because I don't know how to draw R4. So suppose I have an orthogonal set in R3, right? So, well, suppose it looks like this. Okay. And now, so let's say these are my vectors U1, U2, U3. And now suppose I have some vector y that's in R3 as well. Now, because these are perpendicular, in 3 dimensions, you're used to doing this in Cartesian geometry. I can uniquely decompose okay, that didn't look very parallel. So you're used to doing this in, this is just a rotated picture of what you're used to doing in Cartesian geometry. You can uniquely decompose this y into 3 perpendicular vectors, right? That's supposed to be a picture of how you uniquely decompose along 3 perpendicular directions. So here you have a decomposition into 3 orthogonal components. And what are the components? So one of them is parallel to U1, one of them is parallel to U2, and one of them is parallel to U3, right? Well, that's what's going on here, right? Because this first component is parallel to U1. It's some scalar times U1. This is parallel to U2. And this is parallel to, okay, UP. So this is a high dimensional generalization of decomposing a vector into orthogonal components. Okay? So that's what the coefficient, that's what these terms in this formula mean. They have a very clear geometric meaning. And we'll discuss this more. They're formally called projections. We'll talk about that in a moment. So any questions about this? Okay, so now I want to, well, okay, talk about orthogonal projections. So orthogonal projections are really, somehow the killer application, one of the really killer applications of orthogonality and orthogonal sets. And to talk about this, I'm going to need to raise one more definition, which is the orthogonal complement of a subspace. Definition, so given a subspace W of Rn, its orthogonal complement is another subspace. So we'll see in a moment why it's a subspace. Right now, I'll just define it as a set. So its orthogonal complement. Let's see. Is the set W perp, which is a set of all vectors Z and Rn, such that Z is orthogonal to everything in W. Sorry, this is not it's a number. For all Y in W. Okay, so maybe this will become a little bit more concrete with an example. The simple example is, let's consider W to be the span of E2 and E3 in R3. Okay. So so what's W perp? Well, it's a set of all vectors Z in R3, so that Z dot E1, so that Z is orthogonal to every linear combination of these two vectors, right? So that Z dot, I don't know, let's call it C2 E2 plus C3 3 equals 0 for all C2 C3. Yes.
So can Z be in W?
Can Z be in W? Yeah. So I mean, it's a set of all vectors that have this property with W. So you're asking, is there any such Z that's also in W? That's your question, right?
Yes. Yeah.
It's allowed to be.
Okay.
And there is. Can you think of a vector in W that's orthogonal to every vector in W?
Well, the zero vector.
The zero vector.
Yeah.
So it could be the zero vector.
Awesome. Thank you.
That's actually the only one, though, as we'll soon discover.
Okay. Cool.
Yes. Do you have a question? Hello?
Oh, sorry, it was answered.
Oh, sure. Okay, great. So, I mean, okay, one, you can easily see what this is. Being orthogonal to every vector in the span of E2 and E3 is just the same as being orthogonal to E2 and E3 itself. Okay. And okay, that's literally just vectors that are in the span of E1. Sorry, do you have a question? Or no, it's okay. It's okay. So the picture here is that, well, you know, in R3, if I draw R3 this way, and this is the E1 axis, this is the E2 axis, this is the E3 axis, well, the subspace W is, I don't know how this is going to come out, is this plane. So that's W, and W perp is this E1, just the one-dimensional subspace in the direction of E1. Okay. Okay, that's sort of a very straightforward example. But now, well, okay, I mean, since we're doing orthogonal complements, I might as well tell you how to compute them, actually, in general. It's a small, okay, so. Actually, you know what? I'll tell you how to compute them later. Let's get to the key geometric property. So, what's the, this is an interesting question. Suppose I'm given a subspace Rn, and I'm given some vector y in Rn that may or may not be in the subspace. I mean, the interesting case is when it's not in the subspace. The picture looks like this. So I have a subspace W of Rn. Its orthogonal complement is W perp. Okay, I'm just drawing it as a line because in R3, you know, well, we'll talk about the dimensions of these subspaces later, but you can't draw two-dimensional things that are orthogonal in R3. But okay, this is the picture. So this is orthogonal. And now I have this vector y that's maybe not in the subspace. Now the question I can ask is, what is the closest vector to y in W? Let me make this black again. Okay, and this question makes sense because closest, you know, we define distance. We could not have asked this question before this lecture because we didn't define distance of two vectors. But what does closest mean? Well, it means you want some vector y hat in W such that its distance to y is minimum over all choices of y hat. Okay, so that's a geometric question you can ask. If you give me a subspace and you give me some vector that may not be in the subspace, what's the closest vector? Okay, so there's one very key geometric observation here that's inspired by the fact that if you give me a point and a line in Euclidean geometry, the point on the line that's the closest to the point is the one you get by dropping a perpendicular, right? You must have done that in high school. And so here's the key observation. The key observation is, well, suppose I have found this closest point. Let's call it y hat. Well, the observation is that at that point, if I now look at the error vector, so the distance, the vector, the difference between y and y hat, so this is y minus y hat, then this is definitely going to be perpendicular to everything in W. The key observation is at the minimizing of y hat, you have y minus y hat, so this error vector, is actually orthogonal to everything in W. Okay. Now, why is that? Well, let's see a proof of that. So for the proof, let's consider some other vector in W. Let's call it little w. Okay. Okay. Now let's consider the distance of this W to y. So let's draw a line between W and y. And now let's complete the triangle between W, y, and y hat. The key observation is that because y hat minus y is orthogonal to everything in W, this is going to be a right angle. Right? So let's think about that for a moment, right? So imagine it in 3 dimensions with a 2-dimensional subspace, right? If you drop a perpendicular from a point and you look at any other point, it's also going to make a right triangle. So now what happens in this right triangle? Or something quite interesting happens. What happens is that for any other point W in the subspace, the distance from W to y is going to be the hypotenuse of the red triangle. So of the triangle with the 2 sides red. On the other hand, the distance between y hat and y is going to be one of the other sides. Is going to be a side, one of the non-hypotenuse side of the triangle. Of same triangle. Okay, I'm not sure of this. Okay, this color coding is okay. But the key is I'm talking about this red triangle. But now, in any triangle, the hypotenuse is longer than the other sides, right? So this implies that any other such point W must be farther away. So if W is not equal to y hat, it has to be farther away. So y hat, any y hat that has this key orthogonality property must be the closest point. Okay. So I mean, you can prove this. So I mean, you can prove this algebraically using properties of the dot product, but geometric proof is more intuitive. And the concept here is in a right separately. So the key concept is that orthogonality corresponds to optimality. Optimality means being the closest point. Okay, so this is a generalization of this idea of dropping a perpendicular, but to Rn. I should mention this thing, you can do an algebraic proof using the dot product. You can do an algebraic proof like the proof of Pythagoras theorem only using the dot product. But this is the picture that is really important that I want you to have in mind, that the answer to this question is somehow related to orthogonality. What's the closest point? Well, it's the point that has the property in the red box. Okay. Okay, great. Well, how do I compute such a point? How do I compute y hat? Right, so that's what we'll consider next. And let's consider it with a concrete example. Okay. So let's look at an example. Yeah. Let's consider the span of two vectors, which are going to be 1, minus 1, 0, and half, minus 1. These are u1 and u2. This is contained in R3. Okay. And now let's say I have some point that's not in the subspace. So let's say the point 1, 0, 0. Okay. You'd have to check whether it's in the subspace. It's not. So this is not in W, but it is in R3. And now you can ask this question, well, how do you compute this closest point y hat? Right? So the really cool thing that happens now, so here's a picture, there's this W, there's some Y, and I want to compute this point y hat, this vector y hat. Well, if y was in the subspace, then y hat would just be equal to y, right? Okay. And in that case, I have a formula for expressing it as a linear combination of the orthogonal basis vectors. So by the way, these are orthogonal. You could check, right? Which was given on a few slides ago here, right? If you have an orthogonal basis of a subspace and you have something in the subspace, then you can just write it as a sum of these components along those vectors, right? Well, what if I just use the same formula here? Just be the same formula. So let it be u1 dot y for norm of u1 squared times u1 plus norm of u2 dot the inner product u2 dot y over norm of u2 squared times u2. This would be the formula for expressing y as a linear combination of u1 and u2 if it was in the span. It's not. Well, let's calculate what this is. So okay, what's u1 dot y? So that's 1 over, and what's the norm squared of u1? That's just 2 times 1 minus 1, 0. And now what's u2 dot y? Well, that's a half. And what's the norm squared of u2? Well, it's 1 plus a quarter, so that's 3 halves times this vector half, half, minus 1. Okay, so this gives me some vector, which if you calculate this out, you get the vector 2/3 minus 1/3 minus 1/3. Okay. Yes.
Yeah, sorry. I just wanted to ask, how did you get 1/2 and the 1/2 and 3/2?
So the 1/2 should be u2 dot y.
Okay, yeah,
So
yeah.
u2 has a half in the first entry,
Right.
Just half.
Oh yeah, I see.
Is that okay?
If it was in the span.
No. I'm doing this formula even if it's not in the span.
Oh, okay.
So I'm just going to let this happen. So even though y is not in the span, I'm just going to define y hat to be this new vector.
Okay, gotcha.
Okay.
Okay, I see. Yeah.
And now you get this, you see something kind of magical, that actually this vector y hat has the required property that y minus y hat, which is the vector 1, 0, 0, minus the vector 2/3, minus the third, minus the third, is just a vector a third times the vector 1, 1, 1. And if you check this, this actually is in W perp. Right? Because just compute the dot product, just adding 1, 1, 1, and the sums of the entries of U1 and U2 are 0. So actually, y minus y hat is in W perp. So even though I use the same formula, I actually got the y hat I was looking for, right? Because remember, the key property that I wanted was that the difference of this y hat with the original vector should be orthogonal to the subspace. And that's what I got, right? That was the key property on the previous slide. So actually, it looks like the same formula solved this question of finding the closest vector. So that seems kind of magical, but it's actually not magical. It's a theorem, which I'll state as a theorem. It's always true. Okay, why can't I change the color? Oh, okay. Okay, so so the theorem I want to state, one is called the decomposition. What it says is if W is a subspace of Rn, and Y is any vector in Rn, there is a unique decomposition of Y into a vector Y hat that's in W plus a vector Z that's in W perp. So this is the statement. Given any vector, given any subspace W and some vector Y, there is a unique composition into this Y hat vector and some Z vector, where Y hat lives in W and Z lives in W perp. That's just a statement about existence of a unique decomposition. Moreover, if you have any orthogonal basis, then you get a formula in terms of that basis. Okay. The first part of the theorem is just saying there's a unique decomposition. There's no mention of a basis. This is just true for any subspace and its orthogonal complement. But if you do have a basis, you get a formula. For every orthogonal basis, you get a different formula, which always gives you the same answer. Okay. And how does this connect to our original question? Well, what property does such a y hat have, right? Well, think about this equation. If you rearrange it, it implies that y minus y hat is in W of R, right? Y minus y hat is, after all, just z. And so this leads to something called the best approximation theorem. Says that if W is a subspace, y is any vector, then okay, so since we're going to refer to it again, let me just write it here. So I might as well come and say it. So the y hat here is called the projection of y onto W, onto the subspace W. And it's often denoted proj sub W of y. Okay, so with this notation, then what this is saying is then the projection onto W of y is the closest point, the closest vector, sorry, in W to y. Okay. And formally, what that means is for any other vector, in W, the distance between y and the projection is strictly smaller. Okay, so these two theorems go hand in hand. The projection does two things. It gives you this unique decomposition into two components, which are orthogonal. And it also spits out the closest point. Okay. And the reason one implies the other is just this reasoning we did a few slides ago, right? That if you have this orthogonality property, then it implies optimality. Okay. So now let's just prove this theorem. Well, okay, so let's see. You know, the proof is actually pretty straightforward algebra, so I'm just going to leave it to read in the book. Instead, I'll make one more connection to a concept that we studied. So proof of the decomposition theorem. Let me make one more remark, which is that this y hat in the new notation is the projection onto W of y. But by reversing the roles of W and W perp, this Z is actually the projection onto W perp of y. Okay. So that's another way to write it that's more symmetric with respect to W and W perp. So maybe I'll just put this in a separate box. Okay. And one important thing important remark I want to make that people often get confused about is that the projection, you have this formula for the projection, but the actual projection doesn't depend on the basis you use in the formula. In the formula star, which I'll just label here as star. Okay. If you have a basis, you get a formula. If you have another basis, you get another formula. But they both give you the same answer, which is the projection. And the intrinsic meaning of the projection is it's the closest point in the subspace. Okay. That's what orthogonal projections are. Let's see, I guess, okay, I have a couple of more minutes. Any questions? Okay. Okay, so, okay, just to again make a connection with something we wrote earlier, in this decomposition theorem, these components are also orthogonal projections, right? So the first one is the projection onto the span of U1 of the vector Y, and so on. This is the projection onto the span of the vector UP of Y. So this is how these things are all connected. This formula breaks a vector into a bunch of different one-dimensional projections, whereas the decomposition theorem here allows you to do something a bit coarser, that if you have a subspace and you just want to decompose a vector into a component in the subspace and orthogonal to it, then this does that for you. Okay, so one last remark is how to compute orthogonal complements. I said I'd get, right? I'm not sure what's going on with okay. In other words, how do you compute a basis for W perp? Yes.
I just had a quick question for what we just finished.
Mm-hmm.
If the subspace you were working with was like not R3, in R3,
Mm-hmm.
Would your perpendicular still be one-dimensional?
No. So in these, so the question, so these in these pictures, the perpendicular is one-dimensional, just because, I mean, I'm drawing it in R3 and that's what it looks like. But in general, W perp can have any dimension.
Okay, got it.
And that will become clear in the example I'm about to present just now. So
okay, thanks.
It's a good question. How do you compute W perp? Well, let's say W is the span vectors U up to UP. Well, W perp is the set of all vectors Z in Rn such that it's orthogonal to all of them, right? It's orthogonal to the span, but we observed that that's the same as being orthogonal to all of them. So I'm going to write that as U1 dot Z equals 0, okay, and U2 dot Z equals 0, all the way up to and UP dot Z equals 0. Okay. So now what I'm going to do is I'm going to recall that the dot product UI dot Z, I can also write it as UI transpose Z, right? Because dot product is the same as transpose. So what I can do is I can write this in matrix form. This is a set of all Z and Rn such that I can put all of these in a vector, and I get that this is U1 transpose Z, or U2 transpose Z, all the way up to UP transpose Z, equals 0, the 0 vector, right? But now we can write that in matrix form. That's the same thing as saying that that's a set of all z in Rn. Sorry. Of course, these have to live in Rn for this to make sense. Such that I now go back to my high school interpretation of matrix vector multiplication and observe that this vector that with these stacked components here is actually just some A times Z equals 0 for A, the matrix whose rows are U1 transpose up to UP transpose. Okay, so this is kind of a new thing. I spent the whole semester emphasizing that matrix vector multiplication should be thought of as taking linear combinations of columns. But actually now we're going to do the old interpretation, that it's the same as taking dot products with the rows. So by the way, what are the dimensions of A? Anybody know? Yep. Hello? Yep.
P by n.
P by n, yeah, P rows and n columns, right? And I've done something funny here, right? By taking transpose, vectors are column vectors, right? So these are, n by 1 arrays. Now by taking transpose, I've turned them into row vectors, right? So these are row vectors. Okay, but now this reveals now this is in a form I'm used to, right? This is the null space of A. Okay? So to compute an orthogonal complement is actually the same as computing a null space. So let me formalize this in a theorem in hand. So let's state a general theorem. If W is the span of some vectors U1 through P Rn, then W perp is the null space of the matrix that you get by taking the transpose of these vectors and rows. So actually, that means these subspaces and the orthogonal complements are incredibly common. You can generate a subspace and its orthogonal complement from any matrix. How do you do that? Well, we're going to find one more subspace, which is the row space of matrix. So if A is a P by N matrix with rows U1 transpose up to UP transpose, the row space of A is the span of the rows, but viewed as column vector. Right? And then what we just proved, what it really says is that the orthogonal complement of the row space of A is equal to the null space of A. Okay, so this is an easy way to generate tons of examples of different W's and their orthogonal complements, how to compute them. Okay, that's it for today.